We were discussing surface integrals, and in this regard you have seen the definition of surface integrals in the previous lecture. Now, after getting the idea of surface integrals, we will solve some of the important problems based on this surface integral. But before solving a particular problem, I would like to discuss a very important theorem which will be actually invariably needed for the solution of numerical problems based on this surface integral. So what is that theorem and how that theorem can be proved, and then how this theorem will be utilized in solving the problem? Actually, this is the aim of today's lecture. So you can see I have mentioned that theorem here. The theorem says that the normal surface integral of a vector field f over a surface S, which is defined like this: integral f dot n hat ds. You know here n hat is a unit normal vector. You can also write this integral f dot ds simply. So the theorem says that this normal surface integral over the surface S may be written as equal to integral over S1 f dot n hat dy dz over mod of n dot I hat. And similarly, that can also be written as equal to integral over S2 f dot n hat dz dx over modulus of n dot j hat, and that is also equal to the integral over S3 f dot n hat dx dy over modulus of n hat dot k. Actually here you can see I have mentioned that these S1, S2 and S3, what are these? These are actually projections of the surface S on the yz, zx and xy planes. It means S1 is the projection of surface S on yz plane, S2 is the projection of surface S on zx plane, and S3 is the projection of surface S on xy plane. And these scalar products n dot I mod of n dot j and mod of n dot k, in fact these are not zero, these are non-zero. So this is the statement of the theorem. First of all, we will see how we can prove this important theorem. And for proving it, let us consider that the L, M and N are the direction cosines of the unit surface normal vector n hat at a point x, y, z. When you say that these are direction cosines, it means what? It means if you take n hat, let us say in this direction, then it makes an angle alpha with x-axis, it makes an angle beta with y-axis, and it makes an angle gamma with z-axis. Then you know cos alpha, cos beta and cos gamma are known as direction cosines of this unit vector n hat. And these direction cosines cos alpha, cos beta and cos gamma have been denoted by the symbol L, M and N. So you can write this unit normal vector n hat in this way. This is Li plus Mj plus Nk, and instead of L, M and N, you can write cos alpha, cos beta and cos gamma respectively. So I have expressed this unit vector n hat as cos alpha I plus cos beta j plus cos gamma k. And again I am repeating that these angles alpha, beta and gamma are actually the angle made by the unit normal vector n hat, which has been defined at a point x, y, z with x-axis, y-axis and z-axis. So in this way we can express this unit normal vector in terms of the direction cosines of it. Now, see this figure. I have considered here an elementary surface and the area of this elementary surface is, let us consider S. Actually, this is an element of any surface, let us say S, and I have shown the coordinate system here, you can see in this figure. Now, to prove the theorem, we have to find the projection of this ds, which is shown in this figure, in the different planes. So let us first of all see what will be its projection in yz plane. You can see actually the projection of this ds in yz plane will be actually a rectangle. You can see this rectangle. This is marked by A, B, C, D. This is actually the projection of this elementary surface ds in yz plane. Here this AB or CD is parallel to z-axis and AD or BC is parallel to y-axis. And so AB or CD is equal to dz and CB and DA is equal to dy. So actually when you say the projection of ds in yz plane, can you say what will be the direction of this area vector of ABCD? Since this rectangle is lying in yz plane, and you know elementary area vector is always normal to the surface or in outward going, in the direction of outward going normal. So you know, in fact, if a surface is in yz plane, then the unit normal will be in x direction. So its area vector will be in x direction. So if you take the component of the elementary area vector ds in x direction, that will be equal to the area of this rectangle. And see this figure. This is actually the elementary area vector n hat ds, or you may equivalently write it vector ds. And as you know, this n hat or this area vector ds is making an angle alpha with x-axis, that is with the unit vector I. So what will be actually the projection or component of this ds vector in x direction? You can easily say, since this angle is alpha, you know the component of this vector ds in the direction of unit vector I will be simply ds cos alpha. So you can say that this ds cos alpha is nothing. This is simply equal to area of this rectangle ABCD, which is lying in yz plane, or which is actually the projection of this ds in yz plane. So you can see I have mentioned here that this dy dz is equal to what? This is ds cos alpha, and this cos alpha can be written as in this way, mod of n dot I, mod of n dot I. Why I have mentioned it in the form of modulus? You can see, since this n dot I may be positive or negative. It means cos alpha may be positive or negative, because you know when alpha will be an acute angle, then cos alpha will be positive, and if it is an obtuse angle, that is it is greater than 90 degree, then it will be negative. So to take the magnitude of area vector positive, here the sign of modulus has been used. So this is the reason that instead of cos alpha, we do not write n dot I, but we write modulus of n dot I. Now from this equation, you can easily find what will be this ds. You can see this ds will be equal to dy dz over modulus of n dot I. So you can see I have written this ds is equal to this much. Now after evaluation of this ds, you can see that what will be this f dot n ds. f dot n ds. Since we have taken the projection of this ds in yz plane, so that will be simply equal to the first integral, that is this s1 have been taken in RHS because this is projection of s in yz plane. So you can write f dot n ds equal to integral f dot n remains at each, and instead of this ds we have obtained this value, so we'll substitute simply at the place of ds dy dz over modulus of n dot I. So you can see we have obtained that the integral over s f dot n ds is equal to integral over s1 f dot n dy dz over modulus of n dot I. In fact, in this calculation we have considered, or we have taken actually the component of this ds or projection of this ds in yz plane. In a similar way, you can take the projection of this elementary area vector ds in zx plane and in xy plane, and when you will do the same calculation, you can see, you will find that this ds will be equal to dz dx over modulus of n hat dot j when we will take actually the projection of ds in zx plane. And when we will take its projection in xy plane, what will be our result? You can see this will be simply ds equal to dx dy over modulus of n dot k. So in this way, finally you can write that the integral of f dot n ds over the surface S can be written as equal to integral over s1 f dot n hat dy dz over modulus of n dot I, and that is equal to integral over s2. S2 is the projection of s in zx plane, and f dot n dz dx over mod of n dot j, and that is equal to integral over s3. Here s3 is the projection of s in xy plane, and f dot n dx dy over this much. So in this way we have proved this theorem, but I will suggest you in fact the remembering of this theorem is more important than its proof. If you not know its proof but you remember this theorem, there will be no problem in solving the numerical problem. So definitely you should remember this theorem, this result, and after using this result in the numerical problems, definitely you will have an idea of this, and you will find that solution of problem is very easy. So let us consider an example which is actually very important, and after this example you will be acquainted of how to solve the numerical problems based on this normal surface integral. So let us see this problem. The problem says we have to evaluate the surface integral of f dot n ds, where this vector field f is equal to yzi plus zxj plus xyk. And what is this surface S? Actually here the surface S is the surface of a sphere whose equation is x square plus y square plus z square equal to 1. You know, in fact equation of a sphere is x square plus y square plus z square equal to a square, where a is the radius of the sphere. So actually this is the sphere having radius equal to 1, and this surface S lies in the first octant. In the first octant, it means our surface S lies in the first octant, and then we have to calculate this normal surface integral. So now let us see how we can solve this problem using the theorem which we have already studied just now. So let us see. We know We have just seen the theorem that integral over S f dot n hat ds, which may be equivalently written as integral over S f dot ds. You can write it in this way, f dot ds, and this is equal to, you have just seen, integral over S3 f dot n hat dx dy over modulus of n dot k, and let us say this is equation 1. Actually, according to our problem, the surface S is lying in the first octant, and so here actually this first octant has been taken in the xy plane, and so here the projection of this surface S has been taken in xy plane, and you have denoted that projection by the symbol S3. So I have written here integral over S3. So you can say this S3 is what? S3 is actually equal to projection of S on xy plane. Projection of S on xy plane. Now, first of all, we will have to find the unit normal, that is a unit vector which will be normal to the elementary surface area vector ds. And for this, according to the equation of the given surface, let us consider that let a scalar function phi is equal to x square plus y square plus z square. And if you have defined this scalar function phi in this manner, then you can easily find what will be the gradient of this phi. You know gradient of this phi, that is del phi. You know this is just definition of gradient. This is equal to I del phi by del x plus j del phi by del y plus k del phi by del z. And when you will substitute the value of phi here, which is x square plus y square plus z square, and differentiate, then what will be your result? You can see this will be simply 2xi plus 2yj plus 2zk, because this is partial differentiation. So you can easily find this result and say this is equation 2. Now you know that this del phi actually acts along the normal to a sphere whose equation is given like this: x square plus y square plus z square equal to 1. You have actually studied it in the differential part of the vector analysis. So we know del phi acts, this is actually the geometrical meaning of gradient of phi. So according to geometrical meaning of gradient of phi, we can say del phi acts along the normal to the sphere S, whose equation is what? X square plus y square plus z square equal to 1. And therefore the unit normal vector, which we denote by the symbol n hat, you know this is defined as del phi over mod of del phi, because this del phi vector is normal to the surface S, And so to know the unit vector in the direction of this del phi, we simply divide this vector by its modulus. And you can see del phi, we have just defined it in this equation 2. You can see it here. This del phi is what? This is, you can take 2 as a common factor. This is xi plus yj plus zk, and divided by modulus of del phi. When you will take its modulus, what will be the result? You can see this will be 2 times root over x square plus y square plus z square, because vector is 2 into xi plus yj plus zk, and so its modulus will be 2 times root over x square plus y square plus z square. Now you can see this 2 and this 2 will cancel out, and our result will be xi plus yj plus zk and over. Now see the equation of the surface. This is x square plus y square plus z square equal to 1. So instead of this, we will write here 1. So you can see our unit vector n hat, this is simply equal to xi plus yj plus zk. This is your unit vector. And say this is equation 3. Now we have obtained the unit normal vector, so we can define f dot n hat, because you can see the problem. We have to evaluate the surface integral f dot n hat ds. So what will be the value of f dot n? Now you can easily find. So now f dot n hat, in fact you can see your problem that f is given as yzi plus zxj plus xyk. So put it here. This is yzi plus zxj plus xyk and dot n hat, and n hat is equal to this much. You can see it here. This is xi plus yj plus zk. Now take the scalar product. You know, in a scalar product only the similar term is non-zero and all the dissimilar term is 0. So I dot I is equal to 1. So this will be what? This will be x, y, z. But j dot I and j dot k, or sorry, I dot j and I dot k will be 0. Now take the scalar product with zxj. So that will be simply equal to again x, y, z, and all other terms will be 0. And similarly, the product of x, y, k with this will be simply x, y, z. You know it. So this is simply 3x, y, z. So you can see we have easily obtained the value of this quantity f dot n. Now after getting the value of this f dot n, you can see your equation 1 where we have defined this normal surface integral, and so let us put the value of this f dot n in this equation number 1. And in fact we should also evaluate this n dot k first of all, then we will put it. So now first of all calculate the value of n dot k. Again n hat dot k. You have seen just now this n hat is equal to xi plus yj plus zk in this equation 3. You can see. So this is xi plus yj plus zk and dot k, and you can see this will be in fact 0 plus 0 plus z. So this product is simply equal to z. So we have obtained actually the value of n dot k, which is actually positive, also the value of f dot n. So now let us use these values of f dot n and n dot k in this equation number 1, which actually defines this normal surface integral which we have to evaluate. So using these in equation 1. So using these in equation 1, our result will be what? You can see integral over s f dot n hat ds, and this is equal to, you know, integral over s3 f dot n hat dx dy over modulus of n hat dot k hat. Actually, I have repeated the expression here. Now let us substitute the value. You can see this will be equal to integral over s3 and f dot n hat. You can see this is equal to 3xyz. So instead of this f dot n hat, we will write 3xyz, and dx dy over modulus of n dot k. But you have seen that n dot k is equal to what? This is z. So put it here z. Now you can see this z and this z will cancel out, and 3 is a constant factor, so we will take it outside of the integral, and here there will be integral xy dx dy. Now we will actually put the limits here. You can see as the surface S3 is lying in fact in xy plane, so equation of this surface S3, what will be the equation of this surface S3, which is actually the projection of this surface S, since it is in xy plane. So you can write its equation is x square plus y square equal to 1, because for this S3 z is equal to 0. And so to get the value of limits, you have studied the technique of double integral. So you can see, if you will put y equal to 1, then x will be equal to 0, and when y is 0, then x will be equal to 1. So limits for x will be what? This will be 0 to 1. And for getting the limits of y, you can see that this y will be then taken as a variable. So this y will be equal to 1 minus x square root. 1 minus x square root. So y will vary actually from 0 to root over 1 minus x square. This is the technique of evaluation of the double integral. Now let us separate these integrals and simplify it. So you can see what will be our integral. Actually, this will be integral over s f dot n hat ds, and this will be now written as 3 integral 0 to 1 x, and whenever there a integral which we have actually the limits which is not constant but variable, so in case of double integration, first of all we integrate such an integral. So here first of all we will integrate this y, and integral of y that will be equal to y square over 2. This will be y square over 2, and the limits are 0 and root over 1 minus x square and dx. Now simplify it. This is 3 over 2 and integral 0 to 1, and now let us put the limit. So you can see this is x times y square. So at the place of y we will write square root of 1 minus x square. So this will be 1 minus x square, and lower limit is 0, so that will be simply 0, so there is no need to write that. So this is dx. Now you can see this is simply equal to 3 over 2 integral 0 to 1 x minus x cube dx. Now you can see this is a very simple integral. This is 3 over 2 x square over 2 minus x 4 over 4, and limits are 0 and 1. So now put the limit. This will be 3 by 2, and this is 1 by 2 minus 1 by 4 and minus 0. So you can see this is 3 by 2 into 1 by 4, that is 3 over 8. So this is your answer. In fact, the value of the given normal surface integral over the given surface is equal to 3 by 8. So you have seen in this problem that if you have a knowledge of the theorem which we have discussed just now, and how a double integral is solved, if you know these two things, you can solve any problem using these ideas related to the normal surface integral. So in fact in the next lecture we will see some of the more problems regarding this normal surface integral.